Hello, welcome to another practice problem. Today we're going to do problem 8.6 out of the textbook. It says here a beam is subject to equal 6.5 foot bending moments as shown. The cross-sectional dimensions of the beam are also shown. I'll get to that in a moment. But we're asked to find the centroid location, the moment of inertia, the controlling section modulus. We're given a location of H and asked to find the bending stress at that location. We need to identify if that stress is in tension or compression. We also are asked to find the maximum bending stress and then identify if that is as well as in tension or compression. So looking at our moments here, they are acting around our beam in this direction, right? Which is by convention going to create their negative moments, right? So here's our cross-sectional area, and I've already drawn up some information here just to make it go a little bit quicker. So we have our section here, so I've just identified as it member or section 1, 2, and 3, and I've identified a datum, right? So we have a height of 8 inches, and each one of these is a thickness of 1 inch. So there's a couple of ways we can go about this, right? For shape 1, 2, and 3, what we can do is either take, for sections 1 and 3, we can either take them as 1 inch wide and 8 inches tall, and then we would have to cut sections 2 down by 2 inches, because it's 6 inches wide. We'd have to cut it down by 2 inches, and I'll make it 1 inch tall. Or we can do it the other way, and we could say that members 1 and 3 are 7 inches tall, and then this member 2 is 6 inches wide. So what I'll do is I'll just go ahead and say that members 1 and 3 are both 1 inch wide and then 8 inches tall, right? And that's just, there's no reason for choosing that way. That's just what I'm choosing today, right? So that means member 2, right? Member 2 is then going to be reduced to 4 inches, right? 4 inches wide and 1 inch thick, okay? So finding the areas for these, what we can do is say for member 1 and 3, it's 1 inch multiplied to 8 inches, so that'll be 8 inches squared. Member 2 is 4 inches multiplied to 1 inch, so 4 inches squared. Members 1 and 3 are identical, so they'll be the same values. So the centroid for members 1 and 3 are going to be half of 8, so that's 4 inches. 4 inches. And then 1 inch divided by 2 is 0.5, so the centroid from the datum, which I've forgot to mention, is right here. I'll just choose at the bottom. The datum at the bottom, so that'll be 8 inches minus 0.5 is going to be 7.5 inches. So multiplying our area multiplied to y tilde, a lot of people know this is y tilde from statics or whatever. We're just going to call it y sub I. It's the same thing. So area multiplied to y tilde or y sub I. In this case, we're going to have 32, right, inches cubed, and this will be 30 inches cubed, and this will also be 32 inches cubed, okay? So to be able to finish it and do this step here, finding our D value, right? So what we're going to have to do next is find y bar. Y bar, if you remember, is going to be the sum of our y tildes, or our y sub I, multiplied to area divided by the sum of the areas, okay? So in this particular case, we have summing these values here, we get 94 inches cubed divided by sum of the areas, it's 20 inches squared, and so y bar becomes 4.7 inches, okay? So y bar minus y, so we're going to continue with our section here. Y bar minus y, 4.7 minus 4 is 0.7 inches. 4.7 minus 7.5 is going to be negative 2.8 inches. And this is also 0.7 inches. So area multiplied to the distance squared. This should be, sorry for my notation, that should be area distance squared. Squared. That's a 2. Okay. So this should be no, 3.92. This should be 31.36. My calculator work is not working well. This is also 3.92. Okay. And then we'll find our moment of inertias. And if you remember our moment of inertia formula, it's going to be base times height cubed divided by 12. So our moment of inertia for the first one is going to be, which is also the moment of inertia for section 3, is going to be 1 multiplied to 8 cubed divided by 12, which equals 42.586. As you were, I skipped a step. That is 42.67. 42.67. 42.67. And so our moment of inertia for number 2, so our base is 4 multiplied to 1 cubed divided by 12 is 1/3, right? So this is 1/3. And so adding these values together, right? So I should make another box here. It should be I plus AD squared. So 42.67 plus 3.92 should get 46.587. 46.587, and then 1/3 plus 31, we just get 31.6, right? So 69693. Okay, so that's our individual moments of inertia. And what we'll do now is sum all of these together to get our total moment of inertia about the z-axis, right? So we'll sum all of these I sub x values plus our AD squares. And all of those added together, you should get 124.9, and our inches are, or our units are inches to the 4th. Okay, so if you remember, that's 2 portions of our problem statement solved for. So we go back to our problem statement. It says here, find the centroid location, it's our y bar, and the moment of inertia about the z-axis. So that is done and done. Okay, so the next step that we need to do, let me put first let me put a note this, our y bar equals 4.70 inches, and our I sub z equals 124.9 inches to the 4th. Okay, and so the next thing that they're asking for is our section modulus, right? So we're going to have our section modulus about the z-axis, right? So our z-axis and our, we've determined from our datum, so 4.70 inches is our y bar, right? So what we can then say is, okay, well, our diagram shows that our y bar is measured from our datum, right? So this is 4.7 inches from our datum to this point, right? So we need to determine our section modulus, right? And the controlling section modulus, which will be, if you remember from our, let me give myself some room here. From our formula, we'll have stress equals our moment multiplied to y divided by I. But what we've done is said this y divided by I, right? We can just say that this is also going to equal our moment divided by s, where s equals I divided by our y, okay? Which would be our y, I guess our y maximum from the centroid to the outermost edge, right? And so that's our y maximum. And if you remember, and I'm going to just kind of make a relation here, what we're doing here is we're taking a section, right? Let me draw another picture. So we're taking our section, right? We've determined a centroid, right? And then we're going to find this y and this y, right? And the one that creates the maximum stress, that's going to have our maximum, our minimum value. That'll be our section modulus, okay? And this will be similar to, if you remember back when we did torsion, right? We had our shear stress. We had what? Torque C over J, right? This is very similar. We're replacing torque with moment, our C with Y, and our J with I. Instead of shear stress, it's now our normal stress, okay? So these two are kind of similar, right? And so that might just be a relation to help you think about it. So the S values, looking back at what our found values were, we can say, okay, well, our distance from our centroid to the top of the member, right, is going to be 8 minus 4.7, right? So 8 minus 4.7, right? And then this distance here we've already determined is 4.7. Okay, so the greatest distance is going to create our section modulus. So going back over here, we'll say S equals I sub z divided by our y, which then we'll say the top value is going to equal our 124.867 inches to the fourth divided by that 8 minus 4.7, in this case equals 37.8384 inches to the third. And so S bottom then equals the same IZ divided by Y, but this is going to be the distance from the centroid to the bottom of the member, right? So 4.7. So 124.867 inches to the fourth divided by 4.7 inches equals 26.5674 inches to the cube. So our section modulus is going to be the smaller of these two values. So we'll say S equals 26.5674 inches cubed. Okay? So that is now another one of our answers. Let me draw over here our solutions, right? So we have y bar equals 4.70 inches, I sub z equals 124.9 inches to the fourth. Our section modulus now equals, we just determined, is 26.5674 inches to the third. Okay. So now that's part A and A. That's just A. Okay. So part B, right? Oops. That's part A. So part B asks, find the bending stress at point H, right? Which is 2 inches below our centroidal axis, right? So if we look at this diagram that I drew all over, let me kind of clean this up a little bit here. So if we look at H, which is located right here, right? We know this distance, right, is 2 inches. It says so right here, okay? So what we'll do is we'll say to find the stress at H, we're going to say stress at H, or our bending stress, is going to equal our negative moments, right? Because we determined at the very beginning of this problem that we have negative moments. Right? And this will equal negative, our moments were 6.5 kip feet, multiplied to our 2 inches, because that's our y, right? But look at our units. This is in feet, this is in inches, so we need to do a conversion. Let's go ahead and say, 12 inches per foot, and divide this by our I value, which is going to be 124.867 inches to the fourth. So we'll end up with inches squared, kip inches squared divided by inches to the fourth, which will end up with kips per square inch, right? So that'll be, running through the math on this, you should get negative 1.249 kips per square inch. And the negative indicates that we are in compression, so 1.249 kips per square inch in compression. Okay, so we'll go back to our solutions here. For part B, stress at H equals 1.249 KSI in compression. Okay, so part C, right? Part C says the maximum bending stress, right, produced in the cross section. So the maximum bending stress is going to be produced, by the maximum distance away from the centroid. So if my centroid, right, is here, and we determined that this distance here is 4.7, well, 8 minus 4.7 is less, right? Will be 3.3, right? So we know, just based off of algebra, right, you should be able to determine that if I have, from my stress formula, we can say stress max, right? Stress max is going to equal our moment multiplied by y divided by our I sub z. And I'm going to draw an arrow. The larger that this y value is, the larger this stress is going to be, right? So I'm just going to go ahead and make the leap and say that if, because 4.7 is greater than 3.3, right? And those are our distances to each edge. Going back to this diagram, this edge here, this is 3.3, and from here to here is 4.7. Well, then that means that to determine my maximum stress, I'm going to put in my moment, which is 6.5 kips per foot, multiplied to 4.7 inches, doing our unit conversion again, 12 inches per foot, divided by our I sub z, which is 24.867 inches to the fourth. And you should get a stress max. It's going to be, and I forgot, negative moments, right? Stress max is going to be a negative 2.9359 kips per square inch. And so the negative means compression, right? So stress max equals 2.9359 KSI in compression. Okay, and this is part C. And that is the final answer, check mark, and a happy face.